here is the first topic, tangents and normals. So simple, let us first plot a curve. So let's say we have a curve. Some curve like this. Now, at a point on the curve, some point P on the curve, all right, we can draw a tangent to this point. I draw a tangent at this point P on the curve. Okay, and at that same point P, I draw a perpendicular, a normal. So this point PT is called as the tangent or the length of the tangent. Pn is called the length of the normal. All right. Now, so let this curve be y equal to f of x. So y equal to f of x at P is some point, say x1, y1. So slope of the tangent to the curve y equal to f of x at P x1 comma y1 is m is dy by dx at that point x1 comma y1. So from the basic derivatives, the definition of derivatives, we understand that the derivative is the slope of the tangent at that point. Derivative at a point of a function is the slope of the tangent drawn to the curve of the function at that point, as long as the function is differentiable. If the function is not differentiable, this question doesn't arise. So this is the slope. Now, equation of the tangent. Equation of the tangent is y minus y1, point slope form of the straight line, and y minus y1 is equal to m into x minus x1, and this m is dy by dx at that point P. So this is the equation of the tangent. Equation of the normal. What will be slope of the normal? Because normal is perpendicular to the tangent, equation of the normal will be minus the reciprocal of the slope of the tangent. So minus dx upon dy. This is the equation of the normal. And then there is a subtangent, length of the tangent, length of the normal, that we can find out. If I have to find out this. Now, this angle is theta. Now, tan theta is, I drop a perpendicular from here. I'll call this S. So tan theta will be PS upon ST. And sine theta will be PS upon PT. And what is PS? PS is this value y. It is the y coordinate. In fact, the curve can be below the x-axis or below the. So in any case, we just write this as y1 upon PT. Now let's say tan theta is m, slope. Tan theta is the slope of this line, and slope of this line is the tangent to the curve, so that will be equal to m. All right. So tan theta is this. So sine theta by trigonometric ratio, if tan theta is m, sine theta will be m upon root of 1 plus m square. So PT, this is the length of the tangent, y upon m into root of 1 plus m square. This is the length of the tangent, we call. Tangent from the point on the curve to the point where it cuts the x-axis. This is the length of the tangent. Similarly, we can find the length of the normal. So to find the length of the normal, this is 90 minus theta. So again, take tan of 90 minus theta is PS upon PN. From this triangle, tan of 90 minus theta is PS. I'm sorry, it should not be tan, it should be I want PN, so it should be opposite side by hypotenuse, so it should be sine. Just a second. Sine of 90 minus theta is PS upon PN. So we get cos theta is PS upon PN. So PS is y1. Cos theta will be 1 upon root of 1 plus m square, because tan theta is m. Cos theta will be 1 upon root of 1 plus m square. So what we get is length of the normal. Length of the normal, Pn, is y1 into root of 1 plus m square. Of course, because we are talking about lengths, we must emphasize here that we'll have to take modulus, because we have to omit the sign when we talk about lengths. Now, why am I going through this? Because in differential equations, it will be very, very useful. Length of the tangent, length of the normal, equation of the tangent, equation of the normal. You get many questions on differential equations centered around this. Today, we'll take a very simple example, not it is not so intricate differential equation solving, but something very simple based on this concept of tangents and normals. Next, there is something called as subtangent and subnormal. ST is called as subtangent length and SN is called as the subnormal length. So from this equation here, the equation that we have here, ST is PS upon M. Very simple. So subtangent length ST is here. So this length ST is called as the subtangent length, SN is called as the subnormal length. So ST is PS upon M, so Y1 upon M. And because it is length, we take the modulus. And subnormal SN, we take cot. Now we take 90, tan of 90 minus theta is PS upon SN. So cot theta is PS upon SN. So SN will be, I'll just write here, so that tan of 90 minus theta is PS upon SN. So this is cot theta. So SN will be PS upon cot theta, which is PS tan theta, which is PS is Y1, tan theta is M. Okay. So this is, I will write here Y1 into M. So these are the four results of tangents and normals. So we can find tangents to the curves through this. Application in curves and intersection of curves is in finding the points of the angle of intersection between two curves. Angle of intersection between two curves. Okay, the angle, okay, this angle is defined as the angle of intersection between the tangents of the two curves. So we have the first curve here, let's say, and there is a second curve like this, or like this. Now both of them intersect. Now here important, the angle of intersection between the tangents of the two curves, I'm writing, highlighting here, at their point of intersection. This is very important. So at the point of intersection, let's draw tangents. So this is tangent to the first curve, and this is tangent to the second curve. Now the angle between these two is the angle between the curves. So if the first curve is y equal to f of x, and the second curve is y equal to g of x. So how to find the angles? So M1 m1 is dy by dx for the first curve. That means df upon dx, all right, for the first curve. At what point? Let's say this is the point of intersection, P, x1 comma y1. So at P, m2 is dg upon dx at P. And what is the angle? Theta is tan inverse of. Now, if you want to find acute angle or obtuse angle, you can. If you want to choose the acute angle between the lines, then we need to take the modulus. Otherwise, you just leave it like this: m1 minus m2 by 1 plus m1 m2. This is the standard angle between two lines. That result. All right. Now, if m1 m2 is equal to -1, then the curves are set to intersect. The curves are said to intersect orthogonally. Okay, so these are some points for us to keep in mind. Now let us do some simple problems. The line y is equal to 3x minus 2. So we need to find a point on this curve. Curve is x cube minus 2x square minus x. So it's a cubic equation. Now, at which the tangent is parallel to y equal to 3x plus 2. That means, what is the slope? Slope of the line. The slope of the line y equal to 3x minus 2 is 3. Now, let P x1 comma y1 be any point on the curve. On the given curve. Now, let's say if tangent at P is parallel to the given line, if tangent at P to the curve is parallel to the given line, then what? Then the derivative at P to this curve should be equal to 3. So this is what we'll do. So now, so this implies, what is the derivative now? 3 differentiate y equal to x cube minus 2x square minus 1. So we get 3x square minus 4x minus 1 at x1 comma y1 at P should be equal to 3. Let's substitute. We'll get 3x1 square minus 4x1 minus 3, sorry, minus 1 is equal to 3. So what do you get? 3x1 square minus 4x1 minus 4 is equal to 0. So now let us solve this. This is 3 into 4, 12. So with 12 as the factor, 12 as the product, we need the factors to give the sum as -4. The product is -12. So it's product of the extreme coefficients. So obviously we get the, for -12, we get -6 into 2 also gives -12. So this is these are the factors. So upon factorization, we get, of course, in the question, he has not given the interval. So let's see. So we get 2 points, which implies x1 is equal to 2 or x1 is equal to -2/3. Therefore, y1, x1, y1 lies on the curve. Y1 is x1 cube minus 2, x1 square minus x1. Now, if x1 is equal to 2, y1 is 2 cube minus 2 into 2 cube, 2 square minus 2, you get -2. If x1 is equal to -2/3, y1 is -8/27 -2 into 4/9 plus 2/3. We can simplify this. 27 minus 8, 9 into 3 is 27. So 4 into 3, 12 into 2, 24 plus 18. So we get -14/27. So therefore the 2 points are so the points on the curve are 2, -2 or -2/3, -14/27. So there are 2 points on the curve which will have tangents parallel to the line y equal to 3x. Y equal to 3x minus 2. Okay. So this is how we do. This is the application. Concept was very simple. Other things was calculation. What was the concept that we applied? This one. That the tangent at that point should be equal to 3. Others were calculation only. Okay. Next, another problem we'll do. How to do this? Vertical tangent means what will be the slope? What will be the slope for the vertical tangent?
0.
No, that is horizontal tangent. When tangent is horizontal, the slope will be 0. When the tangent is vertical, what is the slope of y-axis?
Infinity.
Infinity. That's right. So, infinity. That means the reciprocal of the slope should be 0. So, dx by dy should be 0 in this case. So, let us anyway try this. Best is what to do. You want to find dy by dx. Differentiate implicitly. So y minus e power xy plus x equal to 0. This is not an explicit function, and it is not easy to make it as explicit function of y in terms of x. It's very difficult. So differentiate implicitly. So we get dy by dx minus e power xy into derivative of xy, and the derivative of xy will be, this is product. So differentiating x, keeping y constant. So 1 into y plus keeping x constant, differentiating y plus 1 equal to 0. Now let us look at this. So collect dy by dx terms. We get 1 minus x into e power xy plus 1 minus y into e power xy. Now dy by dx is 1 minus y, sorry, it's the other way, y e power xy minus 1 upon 1 minus x e power xy. So for dy by dx to be infinity or dx by dy to be equal to 0, this denominator term should be 0. So 1 minus x e power xy should be 0. Okay, 1 minus x e power xy should be 0. This is little difficult. Let us see. X e power xy equal to 1. So xy e power xy, sorry, is equal to 1 upon x. Taking log on both sides, minus log x. So y is basically so it's not a function, by the way. This is not a function. We want that there is a point x comma y which satisfies this equation. X comma y satisfies this equation, this implicit definition. This is, so this is not an equation, this is not a function. It is like this expression is equal to this expression. So from the given options are of course not, I didn't give the options, but the one of the options given is x equal to 1 and y equal to 0. When you do x equal to 1 and y equal to 0, we get this. Otherwise, this is a very difficult function to plot. All right, e power xy. This equals 1 by x. So, but this satisfies, if you can see here, when x equal to 1 and y equal to 0, this equation satisfies. Otherwise, it's a very difficult equation to solve. At this point, now let us see whether this x equal to 1 and y equal to 0 lies on the curve. If you see here, if we substitute 1 comma 0, so y is 0, e power xy, e power 0 plus 1. So e power 0 is minus 1. So this is satisfying. So 1 comma 0 is a point on the curve. 1 comma 0 is a point on the curve. And at that point, the tangent is vertical. at the point 1, 0, the curve has vertical tangent. So of the given options, the options were 1, 0, 0, 1, 2, 0, and 1, 1. And you can substitute and see most of them won't lie on the curve itself. But this will lie, and this equation has to be satisfied. So this would be satisfied by 1, 0, x equal to 1, 0. So this is one. A last example on tangents and normals. So I'll solve this. Say y is equal to a power x. Derivative. Okay. So let y equal to a power x and y equal to b power x intersect at P. Now what will be this point P? x1, y1, let us see. So where do they intersect? You get a power x is equal to b power x. So a power x is equal to b power x. Where will they intersect? A power x is equal to b power x. When is it possible?
X is equal to 0.
Very good. If a and b are two positive and different numbers, this will imply that x equal to 0. So when x equal to 0, this will imply you substitute x equal to 0, a power 0 is 1, b power 0 is 1. It means y equal to 1. Therefore, the point of intersection is P 0, 1. Point of intersection is P 0, 1. Now, differentiate. Now consider the first curve. Let M1 be the derivative of this curve at P. So what is derivative of a power x? It is a power x log a. At what? 0, 1. So substitute x equal to 0. Y term is not there anywhere here. When x equal to 0, you get log a. All right. Similarly, y equal to b power x. Now let M2 be the derivative of this function at P. So we get b power x log b at this point 0, 1. Again, we get log b. So M1, M2 is log b. So what is tan theta? Is modulus of M1 minus M2 by 1 plus M1, M2. So we get log a minus log b by 1 plus log a log b. So which is the correct option? The first option is correct.